Hi there everybody, Mr. Dolan here. I'm going to try to connect Flux and Gauss's law. The last video got pretty long, so I thought I would end it where it was and try to start Gauss's law kind of on its own video, so you can, watch both or one or neither, whatever. So I've taken a couple of examples from the textbook here that are some figures that I think might help us connect what I meant by flux last time in the last video and what exactly is Gauss's law. So typically when we use Gauss's law, instead of using a simple area like the plane, like imagine a piece of paper with lines going through it, instead we're going to talk about a closed area. So instead of just a piece of paper, imagine like a sphere or a cube or a cylinder, or something called a pillbox, which if you don't know, you will soon enough know what I mean. And let's talk about these two closed surfaces I've got here in this these two figures. In the top one, imagine we've got like an egg or something like that, and we've got field lines at some angle, some weird angle. That's what the orange stuff is. Those are the electric field lines. And the weird rounded surface that we see there, you can think of it as the surface of a sphere with just us seeing part of it, or the whole thing being weirdly oblate or whatever. But I want to talk about positions 1, 2, and 3. You can see in the close-up here that each one has 3 different angles. I'll remind you that it's a dot product. And this, by the way, this weird notation here, this integral sign with a circle around it means integral over a closed surface. But if we look at just one field line here in this one unit of area, the issue isn't how many are going through it as much as what's the angle between the area vector, which is always at a right angle to the area, and the E field. So the area vector is the black line, here it's the black line, here it's the black line in this little tiny delta area. And you'll notice that since the area and the E field are the dot product that end up being negative, we would call this negative flux. It's the number 3 over here. Number 1 would be a positive flux. They're in the same direction. The dot product and the area vector, the dot product of the area vector and the E field in the same direction. So number 1 would be a positive flux element. This would be a negative flux element because they're opposite one another. And it's number 2 that's actually kind of significant here because it's going to help us so many times. Anytime the E field and the area vector aren't parallel, well, not just not parallel, but anytime they're perpendicular or orthogonal to each other, there is no flux right there. So we can say that there's flux that's positive when the line is coming out of our surface, flux that's negative when it's going into our surface, and 0 when the surface and the E field are parallel to each other. So again, the parallel in this context means that the orange line is parallel to the surface, but the orange line is at a right angle to the area vector. Don't get confused about what I mean by parallel and perpendicular in this context. The dot product is the relationship between the E field vector and the area vector, which means if those two are parallel, then E field must be at a right angle to the surface, just like the area vector is a right angle to the surface. If these two are right angles to each other, that means the E field's parallel to the surface. So there are no lines going through right there. Here one line is going in, here one line is coming out, here no lines are doing anything. And that's significant. In a few of the examples, if the flux is 0, that's going to tell us something really useful about the situation. If the flux is negative, it'll tell us something useful about it. And if it's positive, it'll tell us something useful about it. Then 24.5 over here, we've got an E field through space. Well, let's consider it in the XY plane. So the E field is all constant and moving through the XY plane. By the way, even though the E field may or may not be constant in this example 24.4, it's all still in one plane. So that's kind of how that was supposed to represent. Same thing here. It's in one plane, the XY plane. So notice in the Z plane, the E field lines are not moving in that direction. They're moving, in this case, from the origin towards positive X. So field lines going through this cube now. So we've got these 4 areas we're interested in. Number 1 is this area in the back. So the E field and the area vector are they're anti-parallel. So if the area vector is going back that way, so in the negative x direction, and E field is going in the positive x direction, then the flux through this little gray, or that's not gray, it's sort of a blue-gray, slate. The flux through this little area here would be E dot dA, so it would be negative. One's going that way and one's going this way. Okay, so if E is coming out of the guy and A is going into the guy, then even though the magnitude of the two of them is such that the angle between them is either 0 or 180, depending on which way you look at it, the fact that the E field's going in, but the area field's going out, means that the flux is negative. Then let's go over here and look at 2. For 2, which is the one on this side facing us, they're both going the same direction, so the flux will be positive. The field line and the area vector are both going the same direction. So the field line's coming out, it's positive. Over here, it's going into this slate-colored thing. The area vector is always going out, but the E field would be considered going in, so they're negative. So negative on that side, positive on this side. Then we'll talk about 4 and 3 kind of together. They're both parallel. And since the E field will be running along this surface on the top and along the surface on the bottom, that means that the area vector for 3 is at a right angle to the E field, so there's no flux. And the area vector for 4 is at a right angle to E field and area vector are at right angle, so it's 0 there as well. So the only flux that would end up mattering would be the flux on this side right here and this one on the back. So on this side, that's both of the sides that are technically in the XY plane, flux is 0. For the one that's in the the XZ plane, there are 2 of those, the one down here and the one up here, flux is 0. The only flux that's going to matter is the one on the back here and the one on the front. And this is the last thing I want to say. Notice that I'm not claiming there's any kind of charge inside this cube. We're just talking about some sort of like imaginary cube that we picked in space, and we picked a region where there's an E field running through it, but there's no charge inside of it. And if we add up all of the different fluxes, the one on top is 0, the one on the bottom is 0, the one on this side is 0, the one on that side is 0. The only ones that aren't are the one coming out here and the one going out there, but they're opposing each other. So the net flux through this closed surface is 0. The reason that is so important is because Gauss figured out, or came up with a way to sort of make this all very clear. If you can end up drawing a closed surface that surrounds a charge or surrounds an area with an E field, you can use its geometry, so its area, to tell you about how much charge is enclosed or what the E field is. So what Gauss figured out, let's get a blank screen. Gauss figured out that if you wanted to, so let's actually write it this way. Yes, flux is absolutely the closed integral over an entire surface of E field dotted with the area vector. But if you can use the symmetry to end up coming up with the area very easily, just using normal, the areas we are used to, then instead of doing any calculus, you'll be able to just write down the area. But let's not get ahead of ourselves. What he said, and I can prove this to you later on, is that the flux is not only equal to this quantity here, and again, we're going to cheat to do the area. It's also equal to the amount of charge enclosed in the surface, so Q enclosed, divided by the electric constant, also known as the permittivity of free space, or just permittivity sometimes. So think about what we're saying here. Think about how fundamental Gauss's little clever trick is. If you can figure out the area of a particular shape that surrounds a particular charge, then you can figure out the E field at whatever point you'd like to. So if I've got a charge right here, and then I imagine drawing a sphere around this, a Gaussian sphere, then that's so bad. That's useless. Let's erase that. In fact, let's switch back over to this guy. So now let's talk about Gauss's law in terms of, let's make sure the dielectric strength is 0. Yeah. So I've got a Gaussian sphere now. Instead of just a sphere, we're going to call this a Gaussian sphere. And we're going to deal with 3 Gaussian surfaces in this class. There are a lot that we could talk about. We're going to deal with 3. One of them is a sphere surrounding an area with either no charge or some charge. One will be a cylinder surrounding an area with either no charge or some charge. And the other one will be, well, it's still going to be a cylinder, but we're going to orient it a little bit differently. So what did I say about the charge or no charge? So in all of the examples we're going to deal with, there's going to be an E field. The question isn't, is there an E field where we draw our Gaussian surface? The question is going to be, is there a charged enclosed? So we're assuming that, like in this scenario, there happens to be no charge enclosed. Well, if we switch back over here, if the charge enclosed, if Q enclosed is 0, then the net flux is 0. That's so much better. So if you can end up, so think about what this means. If you can draw a shape around a particular area of space and there's no charge inside of it, then you know the flux is zero. Or if someone tells you that here's a shape and the net flux is zero, then you know for sure there's no charge inside of it. Okay, so in the next video, I'll actually try to use Gauss's law for a sphere, and then we'll do one for a cylinder and then a pillbox.